Madre mía. Hello. It seems that it works. Okay. La vida.
Well, let's start. Good morning, everyone. Hope you enjoyed the social dinner yesterday. Now it's time to have more fun with physics. This time our first guest is Sergio Ferrando. He's from Valencia. He studied both the degree in physics and his master's specialized in theoretical particle physics here at the Universitat de València. Currently he's studying his PhD at the same university, focusing on extensions of the standard model of particle physics and their phenomenological implications. We are glad to have you here today, Sergio. And now the floor is yours.
Okay, thank you. Can you hear me? Perfect. Okay, so in this talk, I want to talk about effective field theories and left-right models, which are two of the most important topics in current theoretical physics. Left-right models are just a particular extension of the standard model in which I'm working. So this is the outline of the course, of the talk. I want to talk here about how the theories of modern physics are built. So I need to talk about symmetries in physics, the principle of least action. I will explain some things very briefly about quantum field theory, gauge symmetries, and then I will focus on left-right models, effective field theories, and the standard model effective field theories. Effective field theories are just theories that are valid at low energies. This is very easy, I guess. Okay, so let's begin with symmetries in physics. First of all, what is a symmetry? A symmetry is a transformation that leaves invariant some of the properties of an object or a system. For example, here we have a snowflake, and you can see that if we make a rotation of 60 degrees of the snowflake, it remains, in a certain sense, invariant. That's a symmetry, transformation that leaves some of the properties of the object invariant. But here, we are interested in the transformations that leave invariant the interactions between the particles. This is what is important in physics. So, I want to talk here about how to derive a law of nature. It is important to remark that laws of physics will be highly constrained if we want them to satisfy certain symmetry conditions. And as an example, I will use the gravitational potential. Let us imagine that we want to calculate the gravitational potential generated by a mass m2 on a mass m1, which are placed at r1 and r2 respectively, in an instant of time t. Okay, so let's make symmetry reasoning. Imagine that I have the two masses here, and I calculate the gravitational interaction. And then I wait for tomorrow, and I make the same calculation. As far as we know, we will get exactly the same result. The gravitational interaction does not depend on time. This is called invariance under time translations, and it means that the potential cannot depend explicitly on time. Now, I take the two masses, and I move them to another place. As far as we know, this won't change the gravitational potential. Gravitational interaction does not depend on where the masses are. This is called invariance under space translations. And it means that the potential can only depend on the relative position of the two masses. And finally, invariance under rotations. If I change the orientations of the two particles, as far as we know, the gravitational potential is exactly the same. The law of physics doesn't change. So this means that the potential can only depend on the distance between the two particles, right? So we say that this theory is invariant under this thing here. And it is just a name that we use in mathematics. RT means invariance under time translations. R3 is invariance under space translations. And SU3 stands for rotations. And that's all. Probably you have seen something similar when you see the equations of the standard model. OK. We know that the potential energy is given by this expression, which indeed only depends on the distance between the two particles. And we have here the gravitational coupling constant G, which has this value, that we have to measure using in a normal experiment. But in principle, the gravitational potential could have this expression, where there's only a tiny difference between this formula and this one, right? Probably this difference cannot be measured in an experiment because it is extremely tiny. So how do we know that this is the correct law of physics? Well, the point is that in modern physics, in particular general relativity, which is the theory that describes gravity, and the theory that we use nowadays to describe gravity, the symmetry principles are even more natural, intuitive, in the sense that I only have to say, well, the gravitational interaction doesn't depend on me. It is the same, and it doesn't matter if I'm looking at the masses or not, on how I look at them. It is always the same. But this symmetry is very restrictive. We can show that this exponent has to be exactly 1, in a certain limit, but exactly 1. Nevertheless, we still have to measure the coupling constant G. And this is something that we will find also in effective field theories. We will have several coupling constants that are free, that we have to measure, but the laws of physics are extremely constrained. This has to be the potential. There's no other option if we want to satisfy certain symmetries. Okay, so now let's talk about the principle of least action. What is the principle of least action? It is just a formulation of classical mechanics that it is equivalent to Newton's laws. So you can say, okay, if it is equivalent to Newton's laws, why do I have to use it? So it is simple. In this case, it is just because it is easier to study the symmetries of the interactions in this formalism. That's all. There are other advantages, but this is the one in which I'm interested. And this is the principle of least action. From all the possible paths, the particles will follow the one for which the action, which has this expression, where L is called Lagrangian, and that's all, takes its minimum value. And this is a picture. I have a particle in A, which moves to B, and from all the possible paths that it can take, it takes the one for which this thing here, where the Lagrangian, in this case, is just the kinetic energy minus the potential energy, takes its minimum value. And this is completely equivalent to Newton's laws. From this, you can obtain Newton's second law. Force equals ma. But in this case, it is much easier to study the symmetries. Because, for example, we can prove Nether's theorem. And Nether's theorem is probably the most important theorem in all of the history of physics. It says that for each symmetry of a system, there exists a conserved magnitude. Moreover, this theorem also gives the explicit form of that magnitude. So let's go back to the gravitational interaction. We have invariance under time translations. Using Nether's theorem, we can show that this quantity here is conserved. And that quantity is precisely what we call energy. We had invariance under space translation. We can show that this quantity here is conserved. And that's what we call linear momentum. And we had invariance under rotations. We can show that this quantity is conserved, and it is the angular momentum. So the reason why you had to study these three quantities is just because laws of physics are invariant under these three symmetries here. And because of that, these three quantities, which are obtained using Nether's theorem, are important. And the principle of least action also has other advantages, like it can be used to study field theory. And what is a field? It is just a quantity that takes different values for different points of the space-time, like temperatures, for example, which is an scalar field. We also have vector fields, velocities of a fluid, or the electromagnetic field, the electromagnetic waves that are around us, or even matrix fields, let's say matrix fields. And an example of that is gravity in general relativity. It is described by a tensor, but we can understand it as a matrix here. And as an example, don't be afraid, this is the Lagrangian that describes the electromagnetic interactions. From it, we can obtain Maxwell's equations. And this is the Lagrangian that describes the gravitational interaction in general relativity. It seems easy, and it is not so easy, but it seems very simple. Okay, so now I'm going to talk about, very briefly, about quantum field theory. We want to focus our attention on how to describe the interactions between elementary particles. And as far as we know, nowadays, we consider the elementary particles as the excitations of fundamental objects called quantum fields. This is more or less the picture. We have a field that it is extended all over the place, and at some point, it has an excitation, and it is a particle. This is how we unify the idea of, for example, electromagnetic waves and photons. We have a field, an electromagnetic wave, which is all over the space, and it has several excitations, which are precisely the photons. But this is also true for electrons, neutrinos, every elementary particle. Okay, and this is the crucial point. The interactions of quantum fields can also be described using the Lagrangians that we had before. Moreover, and this is very important in our talk, quantum physics highly constrains the set of all possible Lagrangians that we can use to describe elementary particles. They were constrained by symmetries, but they are even more constrained by quantum physics. In particular, if we want our theory to be valid in every range of energies, the Lagrangian can only contain terms with 4 fields or less. That's all. So for example, this is the Lagrangian that describes the interactions of the Higgs field, the famous Higgs field, with himself. As you can see, I have a term with 2 Higgs fields here, 2 Higgs fields, 3 Higgs fields, 4 Higgs fields. I can't put, for example, the Higgs field to the 5th power, 6. No. This is completely forbidden by quantum physics. Otherwise, the Lagrangian will not be well behaved in every range of energies. We can see that if we don't want our theory to be valid in every range of energies, we can do other things. And if you remember, I told you that the Lagrangian was something like the kinetic energy minus the potential energy. This is more or less the same. We can associate this to the kinetic energy, and this will be a kind of potential, which is the famous Mexican hat, which is responsible for the masses of the particles. Okay, that's all about quantum field theory. And now let's talk about gauge symmetries. Modern quantum field theories are based on 2 types of symmetries. One of them is the Poincare symmetry, which is the one associated to special relativity. If I want my theory to describe the interactions of fast-moving particles, like for example protons in the LHC, I need this theory to be consistent with the principles of special relativity. So we need the theory to satisfy the Poincare symmetry, that's all. But we also have gauge symmetries. Gauge symmetries are important because they ensure that our theory is well behaved in every range of energies. If I have a theory whose Lagrangian has 4 fields or less, and also has an associated gauge symmetry, it is well behaved in every range of energy. It is a good theory, right? It's a sufficient and necessary condition. And these symmetries imply the existence of particles that mediate interactions. Photons, associated with the electromagnetic interaction, gluons, the strong interaction responsible for holding together nuclei, and W and Z bosons, associated with the weak interaction, which is responsible for some phenomena like the nuclear decay and other stuff which is more important in high energy physics. But well. Finally, it is important to remark that gauge symmetry implies that these particles should be massless. This is why we introduce the Higgs mechanism. Because if we want to preserve gauge symmetry and we also want to have massive particles, we need to do something. And that something is the Higgs mechanism. Okay, so I will try to explain what is a gauge symmetry using a simple example. I will use the strong interaction. Probably you know that, indeed, protons and neutrons are made out of quarks. quarks are the elementary particles that feel the strong force. There are several types of quarks called flavors. I don't know why, just flavors. Up quark, down quark, strange quark. They have different masses and different charges. And we know from experiments that they can appear in 3 different colors: red, blue, and green. Those colors have nothing to do with the colors that we see. It is just a name, a label. But we also know from experiments that we cannot distinguish between colors of quarks. I mean, physics is invariant under the exchange of color. I cannot measure whether a quark is green, blue, red. It is impossible. As far as we know, it is completely impossible. So, as I have said, physics is invariant under the exchange of color. And how do I exchange colors? I can use a vector which contains red, blue, and green, and I can use a matrix to transform that vector. Then I can take a red quark and transform it into a blue quark. So physics must be invariant under this transformation. We cannot distinguish between the colors of quarks. This is called SU3 invariance. 3 stands for the number of colors, and C stands for color. But this is the crucial point. If it doesn't matter the label that I use to describe a quark, physics should be the same if I use different names at different points of the space-time. Let me explain this. I have told you that quarks are indeed fields. Every elementary particle is a field which is extended all over the place. So in this point, I'm studying a quark and I say, this is a red quark. And then I go to other point and I say, I forgot. What color was this? Let's say that it is green, because physics is invariant under the exchange of color. So it doesn't matter the label that I use. I cannot distinguish between colors of quarks, so it doesn't matter what I have said here. Here I say that it is blue. Okay, but here I use red, I think, and here I have used blue. Is there any problem? I think that there shouldn't be any problem. And this is the case. I can use a transformation that is local. I can put different labels for quarks, red, blue, green, in different points of the space. This is a gauge symmetry, and that's all. It is a symmetry which is local. A transformation that can depend on the point of the space-time. And from this, I can obtain all the physics of the standard model. This is more or less the picture. I have like a rotation. I told you that color is like a vector, and I can rotate that vector in order to have blue, green, and the rotation has to be different, can be different for each point of the space, and that's all. This is the mathematical picture of a gauge symmetry. And gauge symmetries highly constrain the possible terms that we can introduce in the Lagrangians. As I've told you, I cannot put mass terms, for example. Moreover, in the case of the strong force, the only possible free parameters are the masses of the quarks and one coupling constant. This is the same situation that I had in gravity. For example, I had the Newton's capital G and the masses of the particles. Furthermore, Maxwell equations can also be derived using a gauge principle. But in the case of the electromagnetism, I have as free parameters the masses of the particles and their charges. But using Nether's theorem, for every symmetry there's a conserved magnitude, I can show that the electric charge is conserved precisely because I have a gauge symmetry associated to the electromagnetic interaction. And this is very, very powerful. And there are other symmetries of this kind in the standard model. So, okay. What is the gauge symmetry of the standard model? It's this one. This part, you already know this part. It is what I have explained before. And this is associated to something called the electroweak force. In the standard model, weak forces and electromagnetic forces are more or less unified into this symmetry here. And I will explain asymmetry in more detail later. And this is the particle content. We have quarks, which are the particles that feel the strong force mediated by the gluon. Charged leptons, which don't feel the strong force, but they do feel the electromagnetic force. And we also have neutrinos, which only feel the weak force. And finally, the Higgs boson, the famous Higgs boson, which is responsible for the masses of the particles. And this thing here is the standard model Lagrangian, right? No, it isn't. First of all, this term shouldn't be here. I don't know why, but it shouldn't be here. And these are the ingredients to construct the standard model Lagrangian. If I use these ingredients, this symmetry, these particles, I get this. This is the standard model Lagrangian. And I think that there are some terms missing, but this is the point, right? And this is very simply compared to other Lagrangians that we have in extensions of the standard model. So let us study one of those extensions, left-right models. Well, the standard model of particle physics has made the most accurate predictions of all of the history of physics. For example, we have this factor here, which is associated on how the electron couples to the magnetic field, that's all. And this is the theoretical prediction, this is the experimental prediction, this is the error in the last two digits. And as you can see, the agreement is perfect. It is incredible. This is one of the most accurate predictions of the standard model. It is something astonishing. But we know that this cannot be the final theory. Why? Because it doesn't explain some things like dark matter, and we don't know how neutrinos get their mass, for example. There are other problems like gravity, but these are two of the most important ones. So it is necessary to introduce extensions of the standard model. Then we need, for example, new particles and new interactions. And how do we get new interactions? Using a new gauge symmetry. And if you want a good extension of the standard model, you'd better use a gauge symmetry that, in a certain sense, seems intuitive or natural for us. And this is the case with the left-right symmetry. As I've told you, this is the symmetry of the standard model, and it has an L here. L stands for left-handed. This is a left-handed particle. It is moving in this direction, and its spin is pointing in the opposite direction. That's all. But if you take a mirror, if you put a mirror here, you will get this situation: a right-handed particle in which the spin and the velocity are pointing in the same direction. The point is that the W bosons of the standard model only interact with these particles here. This means that the standard model breaks the mirror symmetry. We can distinguish between left and right. And this seems to be very unnatural, right? So we can say, okay, I want an extension of the standard model. So I can use a theory in which there's no distinction between left and right. And how can I get this? Well, I had W bosons that couple to the left-handed particles. I can introduce new W bosons that also couple to the right-handed particles, and there's a symmetry between them. Okay, and in this case, parity symmetry is restored at high energies. These theories also predict, they indeed need, the existence of heavy W right and Z right bosons. Moreover, we also need right-handed neutrinos, which have to be heavy, because, well, the standard model only contains left-handed light neutrinos. But this is a problem with all of the theories beyond the standard model. We need to introduce 5 new Higgs bosons, neutral Higgs bosons, 2 singly charged, and 2 doubly charged. The scalar sector the Higgs potential is it's very difficult. It has a lot of free parameters, and studying these theories is not an easy task, right? But well, we had to do it. In fact, the current bound on the mass of the W particle is this. Its mass has to be greater or similar than 2 or 3 TeV, sorry. And we have to remember that the mass of the heaviest particle of the standard model, the top quark, is 170 GeV. So these particles have to be at least 10 times heavier than the ones that we know. So they have to be very heavy. But, for example, in this model, we can explain easily the masses of neutrinos using the seesaw mechanism. It is very simple. The higher the mass of the right-handed neutrino, the lower the mass of the left-handed one. And this is the formula. The mass of the light neutrino is approximately equal to the mass of the of the Dirac mass, which is a mass of the order of the mass of the electron divided by the mass of the heavy neutrino. And that's all. Indeed, if we want this model to hold, we need neutrinos to be Majorana fermions. They are their own antiparticle. That's all that it means. And there is a famous experiment here in Canfranc, well, in Spain, called NEX, which is trying to prove whether this is the case or not. And this is very important in theoretical physics. We need to know whether neutrinos are Majorana particles or not. Okay, so finally I will talk about effective field theories very briefly, because they are indeed very simple for me. Okay, the extensions of the standard model predict the existence of new heavy particles. And we cannot detect them we cannot detect them because their mass is very high. So we need a lot of energy, E equals mc squared, in order to produce them. But we can study their effects at low energies. So we only need to use a theory that works for low energies. It is only valid up to energies close to lambda, where lambda is the energy associated to the mass of these particles here, these high energy particles. Okay, and I told you, if I want my theory to be valid in every range of energies, I need my Lagrangian to have to only contain terms with 4 fields or less. But now, I only want my theory to be valid up to lambda. So I need to use a Lagrangian in which I have terms with more fields. I is the number of fields, 5, 6, 7, 8. And this is an effective Lagrangian. This is an effective field theory, a theory that works only for low energies. And indeed, these terms with more fields and these coupling constants here are all fixed by the high energy theory. I know the complete theory. The effective theory is just an approximation. So obviously, I can get all of these terms because I only need to know what is my high energy theory and make the appropriate approximations, and that's all. But there's something interesting here called the standard model effective field theory. The standard model effective field theory is a way to study all possible extensions of the standard model at the same time. And the idea is very simple. I know that every theory beyond the standard model contains heavy particles that I cannot measure because they are very heavy. But I only want to study their effects on low energy observables, low energy physics. I know that they will produce these terms here, the same terms that I had before. The only difference is the following one. Since I don't know the high energy theory, I cannot know the value of these coupling constants here. And I also don't know the form of these operators. The only thing that I know is that they have to respect the symmetry of the standard model, because I know that the standard model works at low energies, so this theory has to work at low energies, where the standard model works, so it has to respect the same symmetries. But I cannot know these coupling constants here. The point is that I am studying, indeed, all of the possible extensions of the standard model at the same time. But there are problems. we have a huge quantity of free parameters. Indeed, if I take operators with 6 fields, for example, 6 Higgs fields, there are 59 possible operators and 2,499 coupling constants that are completely free, and we have to measure them. This is a lot. And obviously, the number of free parameters will increase with the order of the operators. But luckily, they are suppressed by powers of the high energy scale. So even though I have a lot of free parameters, their effects won't be important because they will be very suppressed at low energies. That's the point. Okay, so until we find some experiment that contradicts the standard model, we can only put constraints on the free parameters of this method, standard model effective theory. But if we find a discrepancy, we will have a set of coupling constants that cannot be equal to 0. In that moment, we need to study what extensions of the standard model predict the associated operators, and then we will have an idea on what is the proper extension of the standard model that we have to use. But currently, we have to obtain higher order operators in order to have more precision and compare the predictions that we make with these operators with the experimental data. So, for me and for you, there's a lot of work to do. And that's all. Thank you for your attention.
Very interesting talk. Very, very interesting.
Thank
And
you.
now it's time for discussion. If you had any questions. The first one.
Nah. Tell me.
Thank you for the talk, a very nice talk. And you said that we need extensions of the standard model because it doesn't explain a lot of things.
Yes.
Are all those extensions left-right models, or
No, not necessarily.
could you give us an example?
There are, for example, extensions in which you have 2 Higgs doublets, and I think that Carlos works on them.
Yeah.
So this is an example where you don't need an additional symmetry, but just new particles and things like that.
Yeah, exactly. More questions? Well, I have one. Just curiosity. Is there any symmetry establishing that there are only there are free and only free families of fermions in the standard model? What do we know about that?
I don't know if there is a symmetry that fixes the number of families. Probably no, but I don't know it. What we know is that if we want neutrinos, or at least left-handed neutrinos, to be light particles, we can only have 3 extensions of the standard model. And we know that from experiments, from something called the decay of the set boson. And that's all we know. And I think that, I'm not sure, but I think that there's no symmetry that fixes the number of families.
Okay, thank you. More questions? No more questions today. So thank you again, Sergio. And
No, thanks.
a pleasure to have you here. Okay, our second guest this morning is Paolo Martinez. Let me. Okay, he was born in Tudela, Navarra, but moved to Andalucía when he was very young. He studied his bachelor in physics in the Universitat de Sevilla. Then he moved to Valencia to begin his master in nuclear and particle physics with a high intro ICUS grant, and started to collaborate with Benito Jimeno and Daniel Esperante in high-power radiofrequency devices for particle accelerators. Currently, he's developing his PhD in high-gradient radiofrequency accelerating cavities at UVEG and Universitat de València under an FPU grant from the Spanish government. And actually, he's now at CERN for 3 months as part of his PhD program, where he's learning how to design radiofrequency accelerating cavities. It is a pleasure to have you today, Paolo, even in the distance, and now the floor is yours.
Okay, thank you very much. Can you hear me well then? Okay, perfect. First of all, thank you for the very nice introduction. I'm sorry I cannot be there in person with you, but as you said, I am pretty far away right now. And okay, first of all, I would like to thank the organizers for giving me the opportunity of presenting my work. I'm going to talk about the electromagnetism in particle accelerators physics, and concretely, I will talk about the medical applications of particle accelerators. Okay, I will start with an introduction to accelerator physics. Then I will talk about the applications of particle accelerators, specifically about the accelerators in medical physics, and more specifically for hadron therapy treatments. And then I will present our research group, and I will talk about our research. Okay. So a particle accelerator is a machine that is able to generate particles beam with some given properties. For example, you have to choose the kind of particles that you are accelerating, such as protons, electrons, whatever you want. Then you have to choose the intensity of your beam, the shape, the energy, the dispersion, etc. And the main advantage of this is that you can reach a huge energy density. And this is the door to access the subatomic world. So a basic idea of an accelerator is made of a particle source. Then you need acceleration sources, which are mainly electric fields. Then you need guiding and focusing components, which usually are magnets. And then you need your target, which can be from a patient, if you are doing some cancer therapy, to, for example, a painting, if you are doing some research in the components of the things that you are interested in. And then you also need some equipment in order to reach the vacuum levels, the cooling, the diagnostics, etc. Okay, currently there are more than 40,000 accelerators worldwide. And even though it's true that accelerators were born in the 20th century, basically as the tool to do research in fundamental science, in high energy physics, this very small portion right now. Nowadays, you can see that most of the accelerators are used in industrial process and also in medicine. You can see here and here. However, it's true that the biggest advances in accelerator physics are still made in this small portion over here, because it's the field where the most extreme conditions are needed. Some examples of application of accelerators can be found in high energy particles colliders, such as the LHC at CERN, the synchrotron light sources, for example, the ALBA in Barcelona, some material testing properties. An example in the future will be the IFMID-DONES, which is being developed in Granada, or another example could be an antimatter decelerator, such as the ATLENA here at CERN. There are also industrial and medical applications, for example, the food sterilization with electrons, nuclear waste treatment, which is also an application for the future with protons, then medical image, in either for create the radioisotopes for example, PET image, as you can see here, or to create the X-rays beams to obtain image, for example, attack. And also in radiotherapy with X-rays or with heavy particles, for instance, proton or carbon ions. So this is the goal of my talk. I would like that by the end of the talk, we will complete this table together and we will understand the different kind of accelerators that are used mainly. There are other, but they are less used. And I hope that you can understand the different properties of each accelerator. So, how do we design an accelerator? And the answer is with electromagnetism. The electromagnetism is the branch of physics that studies Maxwell equation, basically these four equations over here, and with them we can calculate, for example, the electric field created by a charged particle, the magnetic field created by a wire with uniform current, or for example, a magnetic induction problem of a spire moving inside a constant magnetic field. But there is another important law, which is the Lorenz Force, that tells us how a charged particle moves under electric and magnetic fields. And if we look more into detail in this Lorenz Force, we can split it up in two components. The electric component, which tells us that the particle, a charged particle, will move to lower electric potential energy, and it will gain kinetic energy proportional to the electric potential difference in its movement. So this force, the electrical component, is used to accelerate the particle, as you can see here. And then there is the magnetic force that tells us that the particle will move in circles perpendicular to the magnetic field direction, and it will gain no kinetic energy. So this force is used just to bend the trajectory of the particles. So this is very important to keep in mind, that the electric force is used to accelerate and the magnetic force is used to bend the trajectory of the particles. So the first idea of an accelerator that we can imagine, it will be an electrostatic accelerator. So the idea is basically, I create a electric potential difference and I accelerate my particle with this electric potential difference, like this. So I will use a dielectric belt to transport the positive charge to an isolated electron hosting an ion source, as you can see in this example over here. And for instance, this accelerator can be found in the CIMAM in Madrid. Here you can find a picture. However, these accelerators are limited due to breakdowns. They can reach a different electric potential difference of around 10 megavolts, more or less, at maximum, due to insulation problems. As you can see here, for example, a picture of a breakdown when the potential is too high. So then we have to move to circular machines if we want to reach higher energies. And the first idea is the cyclotron. Cyclotron is based on an alternating electric field and a constant magnetic field. And if we solve the second Newton's law for a particle inside a magnetic field, we can find that this is the force, this is the mass of the particle and the normal acceleration, and we can find that the frequency of the particle moving in circles, in a circular motion, only depends on the ratio of the charge of the particle and the mass of the particle and the modulus of the magnetic field. So there are no dependence on the radius, no dependence on the particle's velocity, and then we can fix electric field frequency here in the gap, and the larger will be the particle's velocity, the larger will be the circle, but the time will always be the same, the time to do one semi-period. You can see an example of the video here. And you see that the electric field and the particle's motion are always synchronized. So the particle will always see the electric field in the correct direction, and it will gain energy, it will do the circle bigger, but the time is always the same. And at the end, when the particle's radius is very high, then it will be ejected. An example of a cyclotron can be found in the CNA in Sevilla. Here you can see a picture of it. And we can say, okay, then if we make a cyclotron big enough and with a magnetic field large enough, we can reach whatever energy we want. But this is not true because, as we know, the massive particles cannot travel faster than light in vacuum, which is around 3 × 10⁸ meters per second. So these equations that we solved before are true in the classical regime, when the particle's velocity is much lower than this speed of light. However, in the relativistic regime, we have to add this gamma factor, the relativistic factor here, and then the particle's frequency in the circular motion will depend on the particle's velocity. You can see that this gamma factor is only relevant when the particle's velocity with respect to the speed of light is large enough. But now we will have a dependence on the particle's velocity, and then the electric field and the particle motion cannot be synchronized for very large velocities. Then we need to move to the next accelerator, which is a synchrotron. A synchrotron is based on a constant radius machine with alternating electric and magnetic field. So I will have my particle traveling around this path, this closed path all the time. I will have an alternating electric field that will increase the particle's energy, and a magnetic field that will keep my particle in this closed path. And you can see that as the particle's energy increases, which is this E over here, the linear momentum of the particle will increase too. So I will have to increase the modulus of the magnetic field as the linear momentum increase, and also we have to increase the frequency of this electric field over here, because the higher the particle's velocity, the lower the time that it will take to do one lap. An example of a synchrotron can be found in Alba in Barcelona. Here it is, the picture. And the limitation of a synchrotron radiation is a little bit more complex idea, because it's based in the fact that a charged accelerated particle emits electromagnetic radiation. So if I have a charged particle that is traveling in circles, it is accelerated because it's traveling in circles, and then it will emit synchrotron radiation. As you can see here, this is synchrotron radiation. Then the particle will lose energy because of this synchrotron radiation, and this energy lost by the particle by turn is proportional to the energy of the particle to the fourth, and divided by the radius of the trajectory and the mass of the particle to the fourth. So this synchrotron radiation will be much more important, for example, for electrons that are much lighter than protons, for instance. However, this synchrotron radiation can be very useful for other fields in science, such as crystallography, spectroscopy, or tomography. And that's why we have a lot of synchrotrons that are just used to produce this synchrotron light. So then, if we want to avoid this synchrotron radiation, we have to move to linear accelerators again. And now we are going to use gaps with alternating electric field in order to avoid these breakdowns due to insulation problems. And we will have some cavities without electric field. So our particle will see always the electric field in the correct direction. And when the electric field is changing its polarity, the particle will be inside this cavity. And we can design these kind of accelerators by selecting the length of the cavities between one gap and the following one. This length will be proportional to the particle's velocity, so you can see that this length is increasing along the time. And then we can also calculate the particle's energy gain per unit length, which is more or less a simple equation. Then when the particle's energy is very high, we need to use RF acceleration cavities, which is just the idea of closing this environment over here in order to create a closed cavity. An example of RF cavity is a microwave that all of you have at home, but the acceleration cavities used in particle accelerators are basically the same idea, but more expensive. You can see here an example with magnetic field and also electric field that is used to accelerate the particle. And you can see that the electric field is oscillating in time, and that's why this is called RF acceleration cavities. RF means radio frequency, so these magnetic field are changing. Okay, so far we focus in the motion of the ideal, the so-called synchronous particle. But accelerators are real-world instruments. So this green dot here is the ideal particle, but we have to know that we will have particles in our beam that are moved from the origin of coordinates, or maybe that have some velocity component in the transverse plane to the particle's motion. And we have to face these discrepancies because we must correct them along the acceleration trajectory. If not, we will lose a lot of particles and we will lose a lot of efficiency in our accelerator. An example of this problem can be found here in a bending magnet, where we have, for example, we will have this bending magnet and we will see the horizontal plane. Okay, sorry. Here is the bending magnet, and we can see that we have a spreading of the beam in the beginning, and then thanks to the magnetic field, this beam is focused. You can see here that the Y of the beam gets smaller again, but however, in the vertical plane, this bending magnet does nothing. So we will have a continuous spreading of the beam, and this can translate into particle losses along the acceleration path. We have to avoid that. Another example is a mismatch bunch with respect to the RF electric field. And you can see that the points, the particles that are outside these blue lines will not get captured by the electric field and will be lost. And the particles that are inside these blue lines will get captured. So you can see that here we have a lot of losses, which are very problematic. So how do we face this problem? We face it with quadrupoles, which are the focusing element in particle accelerators. A quadrupole is just a magnet with 4 poles, as you can see in this picture over here. And then this kind of magnets produce a focusing force in one axis, but unfortunately a defocusing force in the opposite axis. So we have to mix focusing with the focusing quadrupoles in order to create a stable movement in the beam particle. You can see that here is focusing because it's focused in one direction and the focus in the other. And here the focusing means that it's the focusing here, but focusing in the other component. So in the end, the particle's motion is stable. As you can see here, this is the envelope of our beam, and mixing quadrupole and focusing and the focusing quadrupoles, you can keep your beam stable. And you can see that this is very, very similar with the formalism of the geometric optics. We can even substitute the quadrupoles by lenses, focusing and defocusing lenses, and this simplifies a lot the mathematical formalism of these kind of problems. Then there is also a very important technological part in particle accelerators, because they are one of the main technological challenges of science right now. We have to create from superconducting magnets to high gradient RF cavities, ultra high vacuum equipment, beam diagnostics, which are very complicated devices. So this is very important too. And then the summary, we studied the electrostatic accelerator, which are linear, then constant electric field, no magnetic field, limited by insulation problems. Then we have the cyclotron, which is a circular machine with variable radius, constant frequency electric field, and constant magnetic field. But they are limited by relativistic problems. So then we need to move to the synchrotron, which is also a circular machine with fixed radius. The frequency of the electric field must increase with the particle's velocity, as well as the magnetic field, but the modulus here. And they are limited by synchrotron radiation emission. And then lastly, we have the LINAC, which is a linear accelerator with constant frequency electric field. And this is limited by the length, because at the end you have to cut your accelerator at some point, and that will be the maximum energy that you can reach. Okay, so now we move to the medical application of accelerators. Basically, accelerators are applied in medicine in 2 fields: radiotherapy for cancer treatments, and also production of radioisotopes for imaging and treatment. I'm going to put this again. In the case of radiotherapy, typically are used electrons up to 20 MeV, protons up to 250 MeV, and light ions up to 400 MeV per nucleon. Here is just a reminder of what is an electron volt. Is the charge of the electron multiplied by volt, and then is this amount in joules, which can be very short. It can seem very short, but for these light particles, it's quite high energy. This energy is over here. And around 50% of cancer patients in Europe receive radiotherapy. So this is a very common application of particle accelerators in medicine. Then they are also used to produce radioisotopes for imaging and treatment. And these basically are used protons up to 70 MeV, but mainly below 30 MeV, and also light ions, but this is less common. And there are more than 1,000 accelerators in regular use for this kind of application. The kind of accelerators that are used in medicine are basically these three types here. The LINACs are used in medical image and cancer therapy with electrons, and the energy is between 4 and 20 MeV. And there are around more than 14,000 LINACs accelerators worldwide. Then also they use the cyclotron, basically for radioisotopes production and cancer therapy with protons and ions. The energy varies between 11 and 230 MeV, and there are around 1,500 cyclotrons in hospitals. And then the synchrotron, basically for cancer therapy, also with protons and ions, for higher energies than the cyclotron, between 70 and 430 MeV, but there are just a few of them, 89 for protons and 14 for ions. So you can see that from the total of 16,000 accelerators, most of them are LINAC accelerators. Okay, one moment, I need to drink water. Okay, now we focus in the use of accelerators for radiotherapy and the difference between radiotherapy and hadron therapy. So the most common treatment for cancer in using accelerators is the radiotherapy, which is based on using X-rays beam in order to burn the tumor region in the body and kill the cancer in the patient. The problem with X-rays, with photons, is that they have a not very good reposition those curves, as you can see over here. They will deposit a lot of energy in the external tissues of the patient, which are usually healthy tissues, and you want to avoid this. On the contrary, heavier particles, such as protons or carbon ions, have a very different position curve, as you can see here. They deposit almost all the energy in what is so-called the Bragg peak, and this makes them a much better candidate for this kind of treatments, because you can make a much more localized treatment in the tumor region in the body. Besides, they have higher relative biological effectiveness and higher linear energy transfer, which means that the damage caused in the DNA by protons and carbon ions is much more severe than the damage produced by X-rays photons, as you can see in this picture over here. So hadron therapy, which is already a reality, is mainly based on circular machines, cyclotron and synchrotron. The problem with cyclotron is that the energy of the beam is fixed, so you need to use degradators in order to change the energy of the beam. And with synchrotron, you can change the energy of the beam, but very slowly. With these kind of treatments of hadron therapy, you need to change the energy of the beam in order to select the depth of this Bragg peak. So you increase the energy of the proton beam, the Bragg peak will be here. With linear accelerators, you can change this energy much faster, in just 1 to 2 milliseconds. And this is very good if you want to try to treat, for example, moving organs. So you can change the energy of the beam much faster. The problem with linear accelerators is that they must be very long in order to accelerate heavy particles such as protons or carbon ions, and they will not fit in the hospital. So the challenge here is to create a compact linear accelerator that can fit inside a hospital. So there are already some projects in order to create these linear accelerators for hadron therapy treatments. One of them uses normal cavities, which gradients around 18 to 20 megavolts per meter. You can see over here the schematic of the accelerator that they want to build. And there is another project using high gradient acceleration cavities, which are these cavities over here, which can reach a gradient of around 50 megavolts per meter. And this will allow us to decrease the length over here from 11 meters to just 5 to 6 meters. And this is the cavity that we are testing in our laboratory. The problem with these high gradient cavities is that these such a high electromagnetic fields have nonlinear effects. First of all, the very high surface electric field will emit electrons inside the cavity by quantum tunneling, as you can see here in this maker protrusion. And then these electrons will burn the micro protrusion where they are being emitted. And this will produce the evaporation of ion atoms, as you can see here, and it will create a cloud of electrons and ions inside the cavity that will interact with the electromagnetic fields. And this can produce reflection effects, which are so-called RF breakdowns, you can see over here in this picture. And with this process of RF breakdown, you will lose efficiency in your acceleration process. Besides, you will have radiation problems because these electrons that are being emitted will interact with the inner walls of your cavity, and then they will emit Bremsstrahlung photons. And in the outside of the cavity, you will have very high level of radiation dose. Okay, so now I will present our research group and what do we do about this problem and our research topic. This is the picture of our group. There are some people missing, I'm sorry about that, but this is the only picture that I could find. And here our group, we have an high power RF laboratory in order to test this high gradient, the electromagnetic behavior of these high gradient acceleration cavities. So in our facility, it's not an accelerator because we have no proton beam. And then it is also not a treatment facility because we have no beam again. So we just introduce high power electromagnetic fields inside these cavities. And we test the electromagnetic behavior of these structures and the nonlinear effects that are produced inside. This is a picture of the high power sources that we have in the laboratory. This is the schematic. In all this area here, we produce the high power pulses, radio frequency pulses, and then we introduce them in the cavity that we are testing. You can see here. This is a picture of the pulses that we are able to produce, around 12 megawatts, which is very high power. And then we can select the rise time, the fall time, and the length of the pulse. And here inside this pulse, we have the radio frequency, which is 3 gigahertz. Then we also have some diagnostic equipment connected to the cavity that we are testing, as you can see over here. And then with this equipment, we can, first of all, measure the electrons that are being produced here inside the cavity due to the tunneling effect that I told before. We collect them here and here. And with these devices here, we can measure the incident, the reflected, and the transmitted power. And with this signal analysis, we can study, for example, the breakdown localization, the high power behavior, and the dark current, which are these electrons that are being emitted inside the cavity, the dynamics of these electrons. And this is an example of a normal pulse, where we have the incident, the transmitted, and the reflected power, and here is the pulse of dark current electrons. So when we have an RF breakdown, you can see that the pulses are very different. The dashed lines correspond to normal pulses, here and here, and the continuous lines corresponds to an RF breakdown. And you can see that these breakdowns are easily detectable when you compare with a normal pulse. So then we collect all these breakdowns that we are producing in the laboratory, and we use them to analyze the data and trying to understand better what is going on inside the cavity. And then we also carry on some RF conditioning process, which consists of the fact that with these high gradient cavities, you have to start with a very low input power in the beginning, because otherwise you will break the cavity. And then with this very low power, you keep increasing the level of input power slowly, producing breakdowns in a controlled way, until you are able to reach the maximum power either available by your laboratory or you reach the design power of your cavity. And once you reach the maximum with a very short pulse, you increase the pulse and do the conditioning process again until you reach the maximum, and then you do it again for a longer pulse until you reach the maximum pulse length of the cavity. And then you can say that, okay, this cavity is ready to be part of a accelerator if the performance is good enough, or maybe your conclusion can be, okay, no, this cavity is not good enough to be part of an accelerator. And that will be all by my side. Thank you very much. And you have any question, please?
Okay. Thank you very much, Paolo, for your talk. Very, very interesting. Now, some time for discussion. If you have any question, please raise your hand. Okay, one over there.
And thank you for the talk. And you told that to accelerate the particles in a linear accelerator, you need high voltage and high field. So how can you reach that impressive high voltage to accelerate those particles? If you could explain us a little bit.
Yeah, of course. For example, here in our laboratory, we are able to reach around 39 megavolts per meter with this cavity that we are testing. So in order to produce this such a high electromagnetic field, you need a very high input power. And the way to achieve this high input power is made basically with klystrons, modulator and klystrons. So there is like a step process where you first create your pulse with a very low power. Here, oh sorry. Here, can you see the slide?
Yeah.
Okay, so here you first create your pulse with a very low power. Then you amplify it with a solid state amplifier, and you can reach up to around 400 watts. And then you use this modulator and klystron. A klystron is basically an accelerator that works in the opposite regime, in the opposite way. So an accelerator, normally you introduce power to accelerate your particle beam. A klystron is the opposite. You have a beam, you modulate your beam, and then with the modulator is with what fits your klystron, you modulate your beam, and then you extract the energy of your beam, and you obtain an amplification in the RF power very, very huge. So here you can see that at the end of the klystron, here enters around 400 watts, and at the end of the klystron you have 7.5 megawatts. So you have an amplification huge here. So I don't know, with this, this is the klystron that we have in the laboratory. There are bigger and better klystrons which can generate up to 50 megawatts of power, or even more.
Pretty impressive. Thank you for the explanation.
You're welcome.
Okay, more questions? Okay, more than a question, I wanted to make a remark on the importance of all these physics in, for instance, in medicine or whatever applications, because okay, we theorists are working on our stuff, dark matter, CP violation, the Higgs boson, or left-right symmetric models, for instance. But the point is that it's not the particular thing that we are studying. It's what all what we develop to understand those things that may change the society and has a relevant impact on people's lives. So whoever asks you why physics, remember this talk and think about it. And maybe we can finish at this point. Now there's time for coffee break. So thank you again, Paolo, and see you.
Thank you.